In today's lecture, we will learn about universal hashing. So, universal hashing is a technique by which we could do hashing, and the hashing when done in this manner gives provable guarantees about the expected running time of programs. So, let us understand what the basic question is. So, we had looked at the basic data structuring problem. So, typically there are two kinds of data structuring problems. One is the static data structuring problem, whereas the other is the dynamic. In these data structuring problems, we have to essentially maintain dictionaries. Okay, which can answer queries about whether an element is present or not. So, that would have been the static one, but the dictionaries keep changing with time, that is the dynamic data structuring problem. There would be insertions, deletions and other kind of updation operations in dictionaries. The basic operations are insert, delete and find. So, these operations we want to do efficiently, and we know that there is a O log n would be in the worst case deterministic algorithms performance guarantees. So, we can design by means of, let us say, balanced trees, we can do all these operations in worst case O log n, where n is the size of the universe, or you can think of n as the total number of operations that we are doing. So, per operation we are taking O log n. We are interested in knowing whether we can do these in O1. Okay, so, we will see that we can do this in an expected sense if we use hash tables. So, we will assume that, let us say, the keys that we are inserting into these data structures, let us as a concrete example say that the keys are, let us say, character strings of length 40. Okay. So, suppose we knew that our universe basically contains of names of people or customers, and we may assume that each of that is a 40 length string. So, approximately you can say that this is about 10 to the 50, maybe a little more than 10 to the power 50. So, these many different elements make up our universe. So, this is the size of the universe. Okay. But typically our set of interest might be much smaller than that. Okay. So, let us say that the interesting keys are far fewer. So, let us say their size is something like say 1 million, or say 10 to the, maybe a little more than that, 10 to the power 8. Okay. And if you compare the interesting keys with the total possibilities, size of the universe is enormous. Okay. And let us call this by, so universe we will denote by u, and its size is also, let us say we call it as u, and the interesting keys, let us say its size is n. Okay. We will want to store this in a table, okay, and the table should essentially provide us with constant time operations. Okay. So, the basic idea is insert these keys into a table of size, let us say m. Okay. So, m should be approximately O of n, maybe some 10 times n or something like that. The question is, where exactly in the table do we insert? We could assume that the keys are all coming from a sorted universe. Okay. So, these keys, where exactly do we insert in the table is the question. We want to insert in such a way that we can do all our operations in constant time. So, the basic idea is to hash. So, let us see what is a hashing function. So, you can think of it as a function h from u to, let us say, 0 to m minus 1. In other words, given any element of the universe, we are told at which position in the table, which we are going to index by 0 to m minus 1, okay, which is the position where the element x would be inserted. So, if we call the table as A, we will insert x at position A of h of x. Okay. Now, obviously, there are lot of pressing questions. What if multiple elements map to the same position? We had assumed that n is much smaller than, let us say, the total size of the universe, and m is, let us say, something like 10 times n. Okay. So, even if we assume that the table is of size 10 to the power 10, we know that there will be some particular positions which could contain 10 to the 40 different elements. So, that is not going to be a good case. Okay. So, let us first understand what exactly is the issue. So, bad situation, let us so suppose the size of the universe is greater than n minus 1 times m plus 1. Okay. M is the table size. Okay. This would imply that H maps at least, this is for any H, n elements to one position in the array. Okay. So, this is going to be called as a collision. So, there is going to be one particular position where there is large number of collisions. How do we address these collisions? So, a simple technique is called as chaining. Okay. So, we could think of this as the array A containing positions 0 to m minus 1, and this is our universe. Okay. So, each element will via the function h map to some particular position, but the above theorem or lemma would essentially mean that there is some position a lot of elements would map to. Okay. And these could be of size greater than or equal to n. Okay. If the universe is greater than size n minus 1 times m plus 1. Okay. So, at least so you can think of it as u by m elements would essentially be mapping to, there will be one position which contains u by m elements, more than u by m elements. Okay. So, in this case what we will do is, the first element that maps we will write it there, and then we will think of this as a linked list starting from there. Okay. So, all the elements that map to the same position, we will just link it and keep it there. So, this is called as chaining. So, now if any insertions is to be done, we can just go to the start or end of the list and insert it there. If there is a find, then probably it is going to take more time. So, the time taken for the operations is going to be proportional to the length of the chain. Okay. So, if the chain length is large, when is the chain length large? When there are lots of collisions. Okay. So, in those cases the running time becomes large. It could be as large as u by m, and u being a very large collection, u by m and m being small, u by m is not going to be, if there are so many elements mapping to the same position, there is, it looks like there is no escape. Okay. But here what we will see is that randomization helps quite a bit. Okay. So, how does randomization help? As an overview, randomization helps in the same way randomization is of help in the case of quicksort algorithm. Okay. So, if you recall, in quicksort algorithm we were choosing pivots randomly. We could think of, let us say, the pivots being chosen deterministically, and once the code is available, the adversary can look at the code and based on the choices of pivots made, which is deterministic and hence known ahead of time even before the code is run, the choices are clear. So, because of that, the adversary can devise a certain input sequence which will make the algorithm perform particularly poorly. So, the way out was, if the choice of pivot was random, the adversary could not design an input which is bound to take large amount of time while quicksort is being run. Okay. So, random pivots in that sense foils the adversary's strategies of choosing the input cleverly. We will get the same advantage here by randomness. Okay. What we will do is, instead of choosing deterministic hash functions which is bound to have, let us say, pathological configurations. Okay. If you take a deterministic hash functions, it is guaranteed that there are going to be large number of elements which map to the same position. Okay. Whereas, if we randomly choose the hash function, the adversary can't choose a particular dictionary or set of elements which could make the algorithm perform poorly. So, we will see this, I mean, how this works. We will introduce the notion of universal hash functions. So, first of all, look at the properties that we will require of hash functions, and later on we will define what are universal functions. The first requirement would be that the keys are spread out. Okay. So, hash function basically takes the element of the universe and maps it to some position in the table. Okay. So, we do not want too many collisions. So, that is one of the requirements, reduce the collisions. Okay. The second thing, this should be fast to compute. If we had randomly chosen our hash function, that is, each element will map to a random position in 0 to m minus 1, then we can say that chances of collision is going to be very small. But the problem is, if we were to choose one such random function, we need to store that entire function, which is a map from the universe to, from u to m minus 1. That is going to be a very large object in itself. If u was, say, something like 10 to the power 50, we need to store where exactly each of these 10 to the power 50 elements map to. So, storing that table is going to be more expensive than actually maintaining the dictionary. Okay. So, this should be fast to compute. So, we will require, I mean, we will just say that the hash functions takes O of 1 time. Okay. They take constant time to compute. Okay. So, these are the basic requirements of hash functions. Okay. And now, let us define what are called as universal family of hash functions. Some textbooks would refer to what we define as universal family as 2 uniform family. There is a more general notion of k uniform family as well. Okay. So, let us say H is a collection of hash functions from, say, u to m minus 1 say if x and y are elements of u, we call H as universal or universal family of hash function if the probability of H x being equal to H y is less than 1 by m. Okay. So, what is this probability? I mean, what is this event? So, we are fixing some particular x and y, and this should be true for all choices of x and y where x not equal to y. Okay. So, here we will insist that x is not equal to y, because if x was equal to y, then h x is of course equal to h y. Okay. So, probability that h x is equal to h y when x is not equal to y should be less than 1 by m. Now, the probability O is over choices of h. Okay. So, h chosen uniformly at random from script h. So, we have a bag of hash functions, let us say h1, h2, hk, and we have some two fixed elements x and y, okay, or somebody gives you some arbitrary elements x and y. Okay. Now, for every such choice of x and y such that x and y is not equal, if we randomly choose, so uniformly at random pick h, okay, and then apply h to x, you will get h x, and apply h to y, you will get h y. Now, these could be equal, the probability of that should be less than 1 by m. If that condition is met, then this particular collection of hash functions is called as a universal family of hash functions. So, this just provides a definition of what is universal family. We need to worry about whether we can actually construct such families. We will see that we can construct such families where it takes O of 1 time to compute h x for any particular x. Okay. So, we will also see that once we can define such universal families and once we show the existence of such families, we will see that we can do dictionary operations in an expected constant time. Okay. So, first let us see why universal families are helpful, I mean universal family of hash functions are helpful. Okay. So, first theorem. So, this theorem states that if you have universal families, then there are no bad inputs. Okay. So, what is an input here? Okay. When we are thinking of dictionary operations, the set of interesting keys is what we will view as our input. Okay. So, look at any sequence of inserts and deletes, they are over some particular subset of the universe whose size is subset is bounded by n. So, you take any subset of this size, we will show that if we have a universal family, then the insertions and deletions basically happen in constant time. But before we show that, we will show that there are no bad subsets, in the sense the number of collisions is going to be small. So, if H is universal, then for any S subset of U, the number of collisions at x, that means if you pick any element x belonging to the universe, the number of elements that could collide with x is bounded by n over m. So, n being the size of S. This is a simple theorem, but it is a very useful one. This states that for any element of the universe, our hashing function basically was a randomly chosen hash function, let us call it as h. Now, an element x would map to the position h x, and there could be a chain starting at that position. What we want to look at is the length of this chain. Okay. This is less than n by m, that is what we are saying. The expected value is less than n by m. Okay. So, let us see why. So, we should say the expected number of collisions. Okay. So, the proof is straightforward. So, let us say that Cxy is a random variable which takes the value 1 if x and y collide. Okay. So, x and y are two arbitrary values inside the universe. So, this universe had some, let us say x and y are two arbitrary elements. For each of those we will have a random variable Cxy. It takes the value 1 if the random function which we took or the random hash function we took mapped x and y to the same location, then we will say that Cxy equals 1 and it is equal to 0 otherwise. Okay. So, Cx defined as sum over all y Cxy, this is going to be the number of, so here y should belong to S. So, look at S, each element of S can collide with with an element x. Okay. So, our set S was there, we want to know how many of these would collide with x. Okay. That would be nothing but summation over y belonging to S. So, we could look at all elements inside this set. Does this particular element collide with x? If it does, we will get a 1. If this element collides, we will get another 1 and so on. If you add up all these, what you get is Cx. So, Cx is the number of collisions involved at position x when we use a random hash function from H. Okay. So, the expectation of Cx is nothing but summation over y expectation of Cxy. Okay. And expectation of Cxy being an indicator random variable, its expectation is nothing but the probability that Cxy equals 1. So, this is equal to sum over y belonging to S, probability that Cxy is equal to 1, that is same as the probability that x and y collide. So, x and y collide means Hx is equal to Hy. Okay. And we know that for any two element x and y, the probability that they collide is less than 1 by m. So, this is summation y belonging to S 1 by m, which is going to be equal to n, the number of elements inside S, that is n. So, this is n by m. So, if you have a universal family, the number of collisions at any point x is at most n by m. So, that is our take home message. Number of collisions with x, this x could be any element inside the universe, is going to be less than n by m. Okay. And as a corollary, we can claim that all dictionary operations can be done in O1 if universal. So, this is in an expected sense, if universal family of hash functions exist. Okay. That is true just because the time taken for any operation is going to be proportional to the number of collisions, and if we take, let us say, m to be, take m to be O of n, and this entire expression becomes, let us say, some constant, okay, n divided by O of n. So, some constant. So, we know that every dictionary operation, insert, delete, find, etc., can be done in linear O of one time. So, now the next topic would be I mean, this is possible if we have a universal family, but how do we construct a universal family of hash functions? Okay, so we will just need a small recap about the field of integers mod p. Okay. So, what is this? If you look at the collection of numbers from 1 to p minus 1, okay, and we define the addition as addition mod p and multiplication as multiplication mod p, then this algebraic structure has some interesting properties. Okay. So, one is we can do divisions. Okay. So, when we say we can do division means we can divide by non-zero elements. Okay. So, I mean, let us take an example. So, if p is equal to let us say 13, okay, the collection of numbers that we are interested in is 0, 1, 2 up to 12. Okay. Somebody asks us what is, let us say 7 by 3. Okay. If we had carried out this in, let us say, the field of real numbers, then we will get some answer, but here we want the answer to this question, what is 7 divided by 3, to belong to this collection, so that it satisfies all the familiar rules of arithmetic. Okay. So, we can write 7 as 7 into 3 inverse, and 3 inverse is going to be that particular element which when multiplied by 3 gives us 1. Okay. So, 7 divided by 3 we will simply view it as 7 into 3 inverse, and 3 inverse is the number which when multiplied by 3 gives 1. Now, is there any element in this collection when multiplied by 3 gives 1? Well, we can just multiply and see. 0 into 3 is going to be 0, 1 into 3 is going to be 3, 2 into 3 is 6, 3 into 3 is 9, 4 into 3 is 12, okay, 5 into 3, 15, 15 mod 13 is 2, 18 mod 13 is 5, 21 mod 13 is 8, 24 mod 13 is 11, 27 mod 13 is 1. Okay. So, we know that 9 into 3 is equal to 1. Okay. Maybe there are other elements. 30 into 3 is 30 mod 13 is 4, 7, 36 and 10. Okay. What you can observe is that all these elements are distinct. Okay. When you had multiplied the collection 0 to 12 with the element 3, we got all elements in this collection from 0 to 12, and therefore, 1 should of course be present. If we say that all elements from 0 to 12 are present, 1 is also present. Okay. And that is what is true when p is a prime number. Okay. If you take this collection 0 to p minus 1 and multiply it with any alpha in 0 to, I mean, let us say alpha should not be equal to 0. Okay. If you multiply these collections, so maybe we will just start with 1 to p minus 1 and multiply it with any alpha which is not equal to 0, the result will be again 1 to p minus 1, okay, in some other order. Okay. And therefore, you can say that every element alpha multiplied by y, if you vary alpha over everything, then you are going to get 1 for some particular alpha, and that alpha is a unique alpha, that is going to be the inverse of y. This is true when you have this collection as 1 to p minus 1. Okay. In other words, this is a proof that can be made more formal, that every element has an inverse. Okay. So, you can do addition, and additive inverse clearly is there. With any element you can add another element, so that you will get 0 mod p, and multiplicative inverses are also there, means for every element you can multiply with some other element, so that you get 1. Okay. So, since additive inverses and multiplicative inverses are present, we can essentially do arithmetic, all kinds of arithmetic. Okay. Any division would essentially be translated, will be thought of as multiplication by the inverse. Okay. And this is clearly not true when this collection is not a prime. I mean, for example, if you are taken 0 to 99, and if your operations were mod 100, if you take 2, you multiply 2 with any other element and do this multiplication mod 100, the resulting number will be even. In particular, you will not get 1. Okay. So, this existence of inverse is a characteristic of the, I mean, this happens while you are looking at fields, and every element will have a multiplicative inverse. Okay. So, what we will do is we will first describe the family H, and then we will show that that is universal. So, H will basically consist of functions of the form H a comma b. Okay. So, it is 2 parameter family of functions. There is going to be, each function in H is going to be characterized by an a and a b. Okay. So, a b belongs to 0 to p minus 1, a not equal to 0. Okay. And H a b of x is nothing but, say, a x plus b mod p. So, here p is a prime number which is suitably chosen, okay, and H a b comma x is a x plus b mod p, the whole mod m. So, what we do is, for any element of the universe, okay, suppose this is our universe, we will first compute x times a plus b mod p. Okay. So, this will result in a number between 0 to p minus 1, and that number is basically mapped into the array by doing mod m. Okay. So, that maps it to some location 0 to m minus 1. Okay. So, look at all such functions where a is not equal to 0. So, H basically consists of p into p minus 1 elements, okay. Size of H is this much, and each time we run our algorithm, what we are essentially doing is, we are choosing one random element of this function. Okay. So, once we have fixed our dictionary scheme, we will choose a random input, I mean we will choose a random function and then compute it for that, and that random function remains throughout the execution. Okay. So, now we need to look at what is the, I mean, why is this universal? Okay. So, we need to prove, so H is universal is our theorem. Okay, which means what we have to prove is probability that H x is equal to H y, H chosen from script H, this we have to show is going to be less than 1 by size of m. Okay. So, let us call that as small m. Okay. How do we show this? Okay. So, let us fix some particular x and y. Okay. So, first these gets mapped to, I mean, if we are, so we choose a random h, and we want to compute the probability the random h would map these two elements to the same position in the array A. There were m positions that x could have been mapped to, but we are not choosing a random position from this, from this array, but instead we are first mapping x to a x plus b mod p, and this we are going to map to a y plus b mod p, and this mod n wherever, mod n it will take it to this position, and mod n it will mod m will take you to this position, mod m would take you to again this position. Okay. So, whatever we are doing in this two steps, first to z p and then to a, we can think of it as x mapping it directly to this particular position. So, this is our function h. So, h is essentially composition of two functions, and what is the probability that h maps two things to the same position. Okay. So, for x, let us call its image in ZP as R. So, a x plus b mod p, let us call it as R, and a y plus b mod p is equal to R. Here p, we will assume p is greater than m. Okay. Now, this a x plus b, if x is not equal to y, okay, can these two elements, so let us assume that x is not equal to y, can, okay, so a x, so sorry, this is a typo here. So, a y plus b we call it as s. X is not equal to y, can R be equal to s? Okay, let us see if it can be. So, then a x plus b is equal to a y plus b mod p. Suppose R is equal to s, this condition is true. That would imply that a times x minus y is equal to k times p. Okay. Now, a is chosen from 0 to p minus 1, and x minus y also we will ensure that it is less than p. Since these are two elements which are less than p, p cannot divide either of them, and p being a prime must divide one of them. Okay. So, if we choose p to be larger than the, let us say, the maximum values that x and y could take, and such a prime surely exists, if we could take such a prime, then this does not happen. Okay. That is, a x plus b will not be equal to a y plus b mod p. Okay. And therefore, we can assume that R, when you choose x and y as unequal elements, okay, a x plus b and a y plus b are also going to be unequal. Okay. Now, what is the probability that two such elements will map to the same position? That is what we need to compute. So, the intuition is simple: distinct elements x and y map to distinct positions, but x and y could have been adversarial, but now since we have randomized, since a and b are being chosen randomly, this basically is a random element of z. Okay. Let us compute the probabilities. We need to compute the size of the following set: h belonging to script h such that h x is equal to h y. For some arbitrary element x and y, the number of functions which would map x and y to the same element. So, this we can think of as, this is equal to the size of r comma s pairs such that r is equal to, let us say, a x plus b and s is equal to a y plus b, and r minus s is equal to 0 mod n. So, all those r and s, so here when x and y are different, r and s are going to be different. So, 2 r and s will map to the same position only if R mod R minus S is going to be 0 mod n. Okay. So, we need to compute the total number of such pairs. Okay. If you fix an R, okay, so R could be chosen in p ways, R could be any number between 0 to p minus 1, and for each S, okay, for a fixed R, how many S's are there which satisfies this equation R minus S is equal to 0 mod n. Okay, at most p by n. Okay, S could have been p of them. Okay. So, 0 to p minus 1, all those ones which are separated by distance n could fall in the same equivalence class. So, that can be at most, let us say, ceiling of p minus 1. So, the size of this set is bounded by p, p is for the choice of R, and S there can be at most p divided by n minus 1, because R equal to S is something that we do not want, okay. And this is surely less than equal to p into p minus 1 by n. So, we have basically modified some notation. I mean n is m, and that is the size of the table. Okay. So, we were looking at Ax plus b mod p mod m. Okay. So, if R is not equal to S, they map to the same position only if R minus S is equal to 0 mod m. Okay. So, this is going to be 0 mod m, and the total number of such pairs is less than p into p divided by m, the ceiling of that minus 1. So, that is less than p into p minus 1 by n. Therefore, the probability that H A is equal to H B is going to be less than this number, that is p into p minus 1 by n divided by total choices of H. The total number of H were p into p minus 1. So, this is equal to 1 by m. Okay. So, with this we can conclude that H is going to be a universal family of hash functions. Okay. So, basically what it means is we can do all the dictionary operations in constant time. Okay. We will stop here for today.